Okay, so now let's see what happened. Our deployment is completed. I think we have to check kubectl get pods in the namespace longhorn system. And okay, perfect. We can see all the pods are up and running. Everything is done successfully. So now we have to understand these components gradually. I will show you with practical examples what is the purpose of each component. So we can see here, and there is a Longhorn UI. This is the dashboard of the Longhorn. And if I do get deployment, so you can see with the two replica set, the Longhorn UI is deployed, both the pods are up. And if we look into the SVC, the services created under this namespace, so there are multiple services created, and this service Longhorn front end is also a service that is actually created for this Longhorn UI. So this is responsible to show us the dashboard, and this service is by default coming with the cluster IP. What I did, I just kubectl added this service in this namespace, and I changed the type cluster IP to node port. You can expose the service outside the cluster by using ingress controller or by just doing the port forwarding, but I just convert this to the node port so that we can directly access this outside the cluster. So let me just show you. I just open this dashboard, the same port, and this dashboard is by default. There is no credentials, there is no password protection. We can enable this by using ingress controller or some other tools, but this is not our topic. We just have to understand this Longhorn tool. We we have to understand how this engine is working. So we can see here three nodes are up and running. All three are schedulable, mean all three will participate in the storage provisioning and the data replication. Uh, no, nothing is down, nothing is unschedulable. And if we go under the nodes, we can see all these three nodes are under the schedulable. Worker nodes are given in the ready state. So far, no storage is managed by these worker nodes, and 34 GB is allocatable, and only 0.46 GB is used out of 50 GB. I allocated 50 GB. I showed you under each worker node. I created this directory, and by default, this storage is taken from var lib longhorn directory, and that I already mounted with the dedicated hard drive. So 15 GB is reserved. Only 35 GB we can provision for the different persistent volume we will create by using the longhorn. This is the default behavior. The reservation is mean this is for the OS purpose. Maybe OS need this hard drive to write some data, but for us it's 35 GB. We can edit these nodes and we can modify the storage reservations value, and you can see here by default Longhorn use this path and use this disk for the storage purpose. So that's why I added this. Yes, we can add further hard drive too in worker nodes. If we attach more hard drive, we will do this activity, and we can also do the disable of scheduling. For example, I disable the scheduling on this worker nodes. So now this worker node will not participate in provisioning the storage. So there are quite chances you have multiple worker nodes, and you don't want to make every worker node be participated in the storage management. So we can do this activity too. And let me just enable this back, because we just have three worker nodes. Okay, so now you can see here these are the IPs of some pod, and if I go to my pods under this namespace -o white, so here there is an engine longhorn manager, and it's a daemon set on all the worker nodes is running, and we can see 360032024000. And if we go here, we can see the same IPs are reflected here. It's mean the status of these nodes are reflected here, and the management of these nodes in sense of provisioning of storage is the responsibility of Longhorn Manager. So this is the core engine running on each worker node. And we can disable this engine by disabling the scheduling. And what is happening in the back end, when we deploy it, there is a daemon set. Sorry, I will do without -o white. There is a daemon set Longhorn Manager. So daemon set, will automatically create a single instance on each worker node. And there is a deployment uh, Longhorn UI with two replica set. So that is responsible for the GUI, UI resources. So here, if I get the pods, so we understand these two pods and these three pods. So rest of all gradually we will see as we will deploy the persistent volume and persistent volume claim, and we will attach with the pods. Okay, so now we understand these two components. Now we have to understand what type of storage class is created by this engine. Look at the storage class. We can see the Longhorn named storage class is created and is set to default. Okay, so let's start provisioning some persistent volume claim. So for this reason, I just created a very simple persistent volume claim manifest with this name POC persistent volume, and with the storage class Longhorn, and I created with read write many. We can also create read write once. So we will understand the difference in these two, and we discuss the difference in these two type of storages in previous sessions where we discuss the storage class and provisioning or persistent volume. But how this will be different in the Longhorn, we will understand right now. So a 33 GB of storage I will create, and let me just apply this. Apply -f and kubectl get pvc. So you can see the persistent volume claim was in pending state, and then now it's bounded, and automatically the persistent volume is created, and it's 3 GB. So now if I go to different worker nodes, and if I go under the var lib longhorn, and here we can see the directory structure is created. Let me just go to all the worker node. Okay, this directory structure is also created, and this is done by longhorn manager daemon set. So this is also created. Okay, this is done. And if we go under the replicas, so we can see, we should be able to see here the directory that will be created with the name of this PVC. Sorry, the name of persistent volume. This is the name of the persistent volume. So far the directory is not created, because until we are not going to attach this storage with any pod, that storage will not be available on any worker node. So let me just go to, I have a deployment, and this is a very simple deployment. I use the nginx and with the one replica set, and I define the claim, whatever persistent volume claim I created, it will be mounted under the pod slash data with this persistent volume claim. Let me just apply this, and everything I'm doing in the default namespace. So kubectl get deploy. So we can see the pod is trying to create, and on the back end, pod now requested the storage, and Longhorn is now performing some operations in the back end to perform to create the directory structure and the storage. And we can see the directory is created, and the image file is created with 3 GB, and this is just like a hard drive, so it will contain all our data, and all the worker nodes in fact does contain the same image. uh, yes, not the same image mean all the images are of same size, and the replication in between these images are started. So now pod is in should be okay, the pod is in ready state, and if I do execute it this pod and I just run tf-h, so within the pod I can see the storage is provisioned to this pod under the slash data, and it's mounted. Let me just show you the file system too. It's mounted as NFS v4, and it's provisioned from this IP. Okay, so we will look into this IP, what is this IP exactly, and the storage is reached. So let me just do one more thing. I will do an echo hello, and in the slash data file.txt, uh, I'm just going to create a through the touch. Okay, I just created the directory, and let me do ls-l slash data, and a file is created. Okay, let me just create one more thing, a directory, something I want to read from the something I want to write on the persistent volume from the pod. uh, Directory 1. Okay, this is created. Let me just do okay, so we can see something is written in this persistent volume. Okay, now uh, we will understand in that how does this storage reach to this pod. So to understand this, we have to run, I will run the netstat command from the worker node where this storage is provisioned. So let me just first of all get the pod -o wide its own worker node 3. So if I go to worker node 3 and just run this netstat -antup pipesign grep 3260, uh, what is the port number for the iSCSI? Okay, 3260 is not exposed here. Let me just run the same command on worker node 2. It's not exposed here. On worker node 1, but this worker node 1 does contain this port. Mean the worker node is making a connection to 3260, and you know 3260 is the port for the iSCSI protocol to provision the storage. It's mean something is provisioned on worker node 1. Thus, the images I showed you here is just a raw data, but how the pod is reaching, we are going to understand this. So if I do lsplk, we can see an additional 3 GB of hard drive is provisioned by using the iSCSI protocol on the worker node 1. Okay, but there is nothing on lsplk. There is no storage provision on worker node 2. This I added independently as a 100 disk, as a standard disk, but this is not a iSCSI. And lsplk, we can see this, there is also nothing related to iSCSI. So it's mean the storage that is reached inside the pod is coming with the iSCSI and 3 GB is provision. But this is provision on worker node 1. Now if I go to the dashboard, from the dashboard, if we go to the volume, whatever persistent volume we will create will also be reflected here. It will show us the health status of this persistent volume. Mean 3 GB's provision, so far only 114 megabyte is used, and it's bounded with which work which ports are actually mounting using this storage. So let me just do one thing quickly. kubectl get deployment, and I will scale the deployment to I'm on worker node. kubectl get deployment, and I will scale the deployment nginx to replicas 2. So get pods. So now another pod is trying to create on worker node 2, and on worker node 2, let me just get the pod, kubectl execute it and df-h. The data is mounted, ls-ld slash data. So we can see the same data is reflected in this Part-2. So both are sharing the same data. But the question is how the data is reached to these pods. So this is reached just like NFS, we will see this. But before that, we have to understand the concept how this storage is provisioned. So now if I again run the netstat command, so this worker node created a connection to iSCSI port on this IP. So let's investigate which pod does contain the IP, this IP, and that pod will be responsible to provide the iSCSI. If I do get pod longhorn, kubectl get pod -n -o wide, just grab the IP we took from here. So it's the instance manager pod that is responsible to provide the iSCSI storage on the worker node. So instance manager is running on all the worker nodes 1, 2, and 3. And instance manager, if we look into the daemon set, so if you look in a deployment, so instance manager is actually running in the back end provide us the iSCSI storage, and it's running on each worker node. So the worker node, on one of the worker node, the storage is mounted as iSCSI, and then this iSCSI storage is reached to the pod we see in the form of NFS. Let me just do the pod, this command, and dfh. So here we can see this IP is responsible to provide the data within the pod as a NFS mount point. So which IP is this? Now if I do the SVC under this longhorn namespace, so we can see this IP is provisioned by a service named PVC, and both the pods are pointing to the same IP to reach the storage. It means this service is providing the NFS based connectivity to the pod. And if we do a get svc name of the service and hyphen oyaml, or let me just do a describe to this service. So this service you can see is providing 2049, and this is connected with the endpoint, this pod. So let me just investigate now which pod is this in the longhorn that have this IP and its share manager. So what we understand, the instance manager on each worker node is responsible to provision the disk as a iSCSI, and then share manager. This share manager just ran 11 minutes ago when we created this pod, and let me just look into on which worker nodes is it's running. So it's running on worker node 1. So it's running on the same worker node where our storage is provisioned as a iSCSI. It's mean this share manager is taking this storage from worker node 1 and exposing as an NFS share, and by using the service, pods are accessing mounting this as an NFS mount point. So this iSCSI service the iSCSI storage provisioned is reached to the pods by using the NFS protocol, and on the back end of the NFS the iSCSI is created, and iSCSI disk is actually available on each worker nodes and as an image file. So with this way now we understand this instance manager, and now we also understand this share manager. Now let me just quickly do one more thing. I will create one more PVC, for example, of 3 GB, and let me just do kubectl apply -f kubectl get PVC. It's trying to create, it's created. Now in the deployment, let me create a new deployment. Just I'm going to change here because I'm doing in the same namespace. and under the data one, I can say in the data one it will be mounted the PVC one. Okay, so kubectl apply -f deploy kubectl get deploy. So it's trying to create the pod, and on the back end, let me quickly show you what happened. So you can see the another PVC is created, directory is created, and its storage is also provisioned as an image. So this pod, I hope, is ready. It's trying to create. Let me just look the logs. Okay, I think now it's okay, it's provision. So it will take some time because it has to sync the data in all the worker nodes, create the image and replication. So this is created, and now let's see which worker node is running. And now we can see this lsplk. It does contain another 3 GB of disk. So it's randomly, it can decide any worker node to provide the storage as iSCSI, and then it will distribute with the same way. So now if I run the kubectl get pods, in the longhorn system, so you can see the another share manager is ran, and it will be on the worker node that is, both are on worker node 1. So on worker node 1, the SDC and SDD is created, and from here then the pods are using this storage as a NFS, and NFS is responsibility of the share manager. Let me create one more PVC because I am concerned that it should go to other worker nodes too. For example, I'm going to create of this time 8 GB kubectl apply. Okay, it's created. Let me just deploy. Just changing the name and the persistent volume 2, and kubectl apply -f kubectl get pod. It will again create the same thing, but my concern is, let's see, this time the iSCSI will be provisioned on some different worker node. Okay, so this time this worker node 2 also participate to expose the iSCSI, but worker node 3 does not contain any storage. So now lsplk, you can see the 8 GB is exposed here. Now if we look into our pods, so share manager is ran for the third PVC. So each PVC for the read write many will create a share manager, and share manager will actually run on that worker node that is actually having the storage as iSCSI. and we understand that instance manager is responsible to provide the iSCSI storage on diff worker nodes. So now from this worker node to this share manager is exposing the NFS share. And if we look into the SVC, so you can see the three services are created on port 2049, and each service is responsible to provide the storage to the pods using NFS. So let me just quickly kubectl get pods, kubectl execute it. These are from the same. Let me just do here tfh. It's connected with this IP, this one, and the other pod I can say this one. It's connected with the service IP of this one. So now we understand the whole architecture of this longhorn. Mean it is creating an image file on each worker node. It's replicating data across all the worker node. We will see how it's replicating. But so far we understand whenever we are provisioning the storage, it will mount it. It will expose it as a iSCSI storage on some worker node, and then from that worker node, it will be reachable by NFS storage to, to the pods. That's why when we install the Longhorn, we look in the dependencies that NFS v4 client is mandatory on all the nodes that will be used the storage. So here on this dashboard, what happened now? We can see all three storages volumes are reflected here, and from here you can also look that this storage is mounted with these two pods, and this is only for one pod. And whatever I dig down from the worker node by running these commands, you can directly go to the dashboard, and this dashboard will explain you that this storage is actually exposed as iSCSI on worker node 2. This is on worker node 1. This is on worker node 1. That's why we can see on worker node 1 2 devices, and on worker node 2 8 GB device. So this is also a good way to look this. And if we click on this volume, so you can see its healthy status, mean it's replicating across all the worker nodes. And where it is replicating, you can see worker node 1 under this directory, and instance manager is taking care of the replication. And go down, we can see how many, what is the name of the persistent volume claim that was responsible to create this storage, which pod is using pod status, everything is mentioned here. Okay, and we go back to the volume, and we can just update the replica count. So replica count means this data will be replicated to all three worker nodes. It will be available on three different worker nodes. So we can reduce and increase in case we have more worker nodes. So this is the default value. And now this is done, we understand how pods are reaching to these. So let me just quickly show you. If I go to, I write some data in one of my disk that was created under the var lab longhorn, and under the replicas and ls minus ltr. Let me see the very first one we created, this one, and this is the image. So if I try to mount this image under some mnt and tfh, I just mounted this as a device under the mnt, the image directly. If I go under the mnt, so I can see the same data what is inside the pod. So it's mean this image file does contain all the data. And if I just mounted this image to show you what is actually happening. And if you mount the image on the other worker nodes, you will see the same data. So the responsibility of doing the replication is by Indian image EI, manages the actual data operations, read, write, and replication. Whatever you will write in the pod, it will go by NFS to the iSCSI that is exposed on the one worker node, and then Indian image EI that is running here will be responsible to do the replication across all the worker nodes. So in case we lost one worker nodes, we can get back our data. Okay, so we did this. Now we have to, now let me just do get deploy, and we are running this one. So now we have to, we test how it is working with RWX with multiple pods, and different worker nodes can reach this by NFS. Now let me create how read write once is working with this storage class. So let me just let me first delete this deployment. So deployment is deleted, and let me get the pods in the Longhorn namespace. So when I will delete this, it will also delete the share manager. So if I get deployment, let me just delete the deploy remaining of the deployments. So you can see one of the share manager is removed because the NFS, no more NFS is required in the pod. And I will delete nx2 to get the deployments are deleted, and this share manager will also be removed automatically. Okay, so now and the services, yes, the services I showed you are also will also be deprovisioned automatically after some time when we are going to delete the pods. So okay, the pods are deleted. Okay, so now uh, I am going to create a persistent volume claim by using the same storage class read write only. Sorry, read write once. Only one pod can write the data. So in the deployment kubectl get PVC, we already have the PVCs uh, Okay, let me just modify this PVC to, I can say PVC RWO just to make a difference. kubectl delete apply PVC, get the PVC, it's pending, it's created as read write once, and in the deployment I will use this persistent volume claim and just leave it as nginx2 and let's see how it will work. kubectl apply -f this deployment and get deployment, get pod is trying to create. Let's describe this pod to see what is happening on the back end. Volume attached successfully. Okay, great. And it should be available in a while. Okay, great. Now it's running. So what happened on the back end, the storage is again created, replicated on the all the pod, and it is exposed where it is exposed. If I go back to my dashboard and just refresh, so I can see this new storage. This is detached. Detached mean it is not connected with any pod, and this healthy mean it's connected with the pod. This is I just created, and it's exposed as iSCSI on worker node 1. If I just go to worker node 1 and I simply run the command to get the connectivity with iSCSI, so you can see rest of the worker nodes are not providing any iSCSI, but this worker node is only providing iSCSI, and we see this which pod is actually responsible, and LSBLK, the 8 GB is exposed here, but this time the difference is it's mounted somewhere, and if we go and if we look into the pod, uh, execute it this pod tf-h. So here you can see it's not mounted like NFS. It's mounted as straightforward a device, and it's exposed on the server, and it's mounted somewhere under for the pod. So remember, whenever you will create the read write once, it will only be exposed on that pod where as iSCSI on that worker node where the pod is actually running. So let me just to show you kubectl get deployment. If I try to do a scale this deployment replicas to 2 and get deployment and get pod, we will see the another pod will not be alive because it's read write once, and hyphen pod hyphen white, it's going on worker 3, and if I describe this pod, we can see some error, that multi-attach error from volume. This we understand in the previous videos, but this persistent volume is not reachable by worker node 1, worker node 3, because worker node 1 already occupied this. Okay, so the Longhorn is not using the NFS. It's straightforwarding creating the pod on the worker node where the pod is created. The storage it will provision where the pod is created. So let me just do one more thing. If I do kubectl get pod and I will scale the replica to 1, get pods, and it's running, and let me create one more persistent volume claim. Again 8 GB, okay, it's good. kubectl apply -f, ctl get pod, get pvc, and kubectl, and I will use this in the deployment. Let me set this to nginx 3 because I'm working in the same namespace. Just I'm going to change here the claim name kubectl apply kubectl get deploy and pod -o and it's creating now on worker node 3. It's mean the storage will also be provisioned as a iSCSI on worker node 3. So I created this another deployment just to show you on the dashboard. Even you can see the second healthy one is attached on worker node 3. So if we go on worker node 3 and again run this netstat, we can see it's attached. lsplk, it's attached. The pod is also running on the same machine, and pod and kubectl execute it, this one on worker node 3 tf-h, it's mounted, and it's also provisioned on the same worker node. So just we understand that if this is RWO, it will only provision on the same worker node and no NFS will be used. But for RWX, it will be provisioned on any worker node and then it will be distributed to different worker node by using the NFS. So we understand this concept, and we now we have to take a look on the different components once again. kubectl get namespace, get pods in the namespace. So csi-attacher, what is this engine? It's running on all the worker nodes. So this is actually, I just wrote the definitions here. So csi-attacher is responsible to provide the storage to pods using volume attachment custom resource definition. If I just look, the custom resources kubectl get volume attachments. So far two volume are attached on worker node 1 and 2. So wherever the volume will be attached as iSCSI, this will be the responsible engine. Similarly, csi-provisioner watches for persistent volume claim and deletion. csi-provisioner will be looking to our deployment of manifest of persistent volume claim, and then it will automatically create the persistent volume on the back end and will create and delete the storages. Then csi-resizer, we can also extend the size of the storage. Like if I go to any this storage 8 GB, okay, let me just try to, we can expand volume from 8 to 10 GB. So it will be updated in a while. Now it's expanding, and on the fly the pods will be able to get the more storage. So this is the responsible of csi-resizer. Okay, we can also take snapshot uh, by to create any specific footprint of your storage. And so where we now understand all these components, we understand engine, image EI. So engine image EI, we understand that manage the actual data operation, mean all the replication in between all the images created on specific location are also are managed by this engine. Instance manager, we understand provisioning of iSCSI on the worker nodes. Okay, this is a CSI container storage interfacing plugin. Uh, the container storage interfacing we discuss in detail in our previous videos of Kubernetes. You can see that. So this is mandatory whenever you are going to provision any storage class or any specific type of storage on your cluster. So CSI drivers are mandatory. So these are providing the drivers to each worker nodes. And manager, we understand the UI. So this is all done, and you can see it's 10 GBs now. And if we go in this pod, we can see the storage is expanded on the fly. And in the nodes, we can see uh, how much is provisioned, allocated, and how much is actually used. So you can see this is just like a thin provisioned, and this is showing actual how much we allocated. So far we allocated up to 32 GB. Okay, and now this is done. So in the next video, I I will explain you about the failover. If we lost one of our worker node, how we can recover our data and how the pods will be relocated, and automatically the storage will be relocated to other worker nodes. And we also have to understand, if we are going to expand the storage on different worker nodes, we want to add more hard drive. So how we can go to different nodes, and from here edit the nodes, and from here we can add more disk, so it will increase its capacity.